I really think now is the most exciting time to be a materials scientist and engineer in aerospace because of all of the amazing, amazing opportunities there are for using materials or looking at materials in different ways for different applications, not just on Earth, we're talking moon, Mars, beyond, right? And so that alone, I think it's just a very, very exciting time to be in materials.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE Company Database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below. And now, let's get on to the episode.
Hey everyone, we are excited to welcome today's guest, Dr. Valerie Wiesner, a research materials engineer at NASA. We've been waiting to do an episode for quite a while, and so we're so happy to have her here today. Valerie earned a PhD in materials engineering at Purdue, where she researched high-temperature ceramics with the goal of making space travel more routine. She then went on to conduct materials research at two different NASA facilities, Glenn Research Center and Langley Research Center. We are very lucky to have Valerie joining us today, because she has experience working in both aeronautics and in space research within NASA. Thank you for joining us today, Valerie.
Thank you so much for having me.
Yeah, so basically, we've been really excited about this because I think just in general, working at NASA is maybe a dream for so many people, especially like materials engineers. So we were just wondering if you could go through your journey and tell us more about yourself and your path to eventually becoming a research materials engineer at NASA.
Yeah, definitely. So my disclaimer will be that, it is not a requirement to work at NASA to know that you want to work at NASA from an early age. That just happened to be the way it worked for me. Sharing from my experience, I've always been really mystified by space travel and exploration. And, I can remember as a little kid seeing the shuttle fly, right? So, and getting to see that, regularly on TV or just knowing about it and, that there's a lot of really cool space exploration taking place was something that really piqued my interest. And I really was super into astronomy. I'd say stargazing was kind of the gateway for me to get really into space. From an early age, I would follow, as I would take advantage of as many opportunities in STEM, science, technology, engineering, and math to really help me kind of cultivate and develop, my interest really, right? My passion for space. What's kind of interesting is that for me, I know we're materials scientists and engineers here, but what's kind of funny is for me, it didn't start out that way. Back when I was in undergrad, I actually had the intention of pursuing a career in astronomy. I was pretty sure that that's what I wanted to do when I grew up. I wanted to be an astrophysicist and work at NASA, right? I actually really dove headfirst into astronomy. And so I was able to take advantage of some opportunities at my college. It was Carleton College in Minnesota, really great program in physics and astronomy. And so I was able to do hands-on research in astrofields. I was able to go travel even to different observatories to collect data. And I really enjoyed it. Though what's kind of funny is after my freshman year, on a whim, I found an internship opportunity. So those of you in undergrad and grad school might be familiar with the term REU, Research Experiences for Undergrads. So it's a really great opportunity for undergrads to kind of dive into a program at a university and learn about research firsthand. And so for me, out of my freshman year, I kind of applied to a bunch of different opportunities, not really expecting, which one would really pan out, right? And one of the ones I happened to apply to was in materials engineering. Go figure, right? And it was actually at Purdue University, which you might recall is where I ended up getting my PhD from. And so that summer after my freshman year, I got exposure to ceramics. And it was really my first encounter with materials. And so for me, I really valued the more hands-on experiments that I was getting to do in lab. And what I really piqued my interest with ceramics, especially the ones that I ended up studying, were that they had an opportunity for use in space applications for space vehicles, for reentry and those kinds of applications. And so to me, I found that really fascinating that, these material systems that different people are looking at could help enable space transportation. And so for me, that's really what hooked me. A couple years later, I ended up, as you know, long story short, I guess now at this point, I pursued a PhD in materials engineering, specifically in ceramics. And so I just share that because it's kind of a funny aside, that even though I knew I wanted to work at NASA, the position I ended up getting wasn't exactly as an astrophysicist. So now I'm a research materials engineer. That process, there are of course a variety of ways you can get employed within NASA. And for me, the way it worked out was towards the end of my graduate career, I applied to a pathways internship. And so a lot of people hear internship, they think kind of a short-term deal. The pathways internship program is actually a little different in that it resembles more of a co-op, if you guys are familiar with that. And so what that enabled me to do was to kind of work as a student part-time for a summer at NASA Glenn, where I got hired as a pathways intern, kind of try it out, see if it was a good fit. And it ended up working out for me that after the conclusion of, me graduating and kind of finishing the pathways program, I was offered a full-time employment. So that's kind of how it worked out for me, that I was able to kind of get hired in through that pathways program. So yeah, and been loving it ever since.
Yeah, that's awesome. I have so many questions about your journey, but I guess the most important one maybe is, do you have any advice, or what was the process like for that NASA Pathways internship in particular, in the application process?
Yeah, so what's kind of funny is the program, I'd say, at least to me, I didn't know about it as a student. I'd never heard of it. And so I was kind of positioning myself to get a postdoc after I completed grad school, with the intention of hopefully getting, a government postdoc position, preferably at NASA, and hopefully getting hired there. But if not, positioning myself for other opportunities as well. And so when I actually was connected with a researcher at NASA Glenn, she told me about this program initially as oh, this would be a good option if, you want to have an opportunity to actually get a career, a job, right, at NASA, as opposed to a postdoc. And I was kind of like, what? Tell me more. And she told me it was a co-op. And, I was in the last year or so of my PhD, and I actually said, oh, I don't know if I want to do a co-op. I have to graduate, because in my mind, that was what was pressing, right? Not really understanding the program itself. And so ultimately, after some great conversations with my advisors and learning more about the program, I realized that yes, actually, the program itself is a really great opportunity to get your foot in the door at NASA. What's interesting about it is, with a lot of co-op programs, is instead of being treated as a student, you are treated as an employee, as a civil servant, effectively from day one. You get sworn in on your first day. So that begins kind of like your time of service clock within the government. And it also allows you, of course, to get to know the people that you will hopefully be working with long term, learn more about, your center, the agency, all of those kinds of things. And so it's a really, I think, powerful program that I think more and more people are learning about now. But I do want to make sure people know about it. It is a little different from the traditional NASA internship in that it is really a pathway to a civil servant position. If both parties, of course, agree, right? Because at the end of the day, after you graduate, you're a new supervisor and you have to really figure out it's a good fit to land the job. But odds are usually it's a really good opportunity to pursue a career at NASA. That's kind of how it worked for me, at least.
That's awesome. And I'm sure during those conversations and also previous conversations about, oh, should I do a co-op or should I do an internship? One question you may have thought about was whether or not to go straight to industry or even go to PhD, because I know a lot of times some people go co-ops and they just never finish their PhD altogether. So I guess moving back a step, could you maybe walk us through your decision about how a PhD was right for you? And then what role did it, I mean, you got the co-op while you're a PhD, so kind of how that played out. And then maybe in the end, how a PhD differs from research at NASA, because I'm not quite sure any of us have a great idea about kind of the workflow of NASA, because I know I want to work for NASA, but I don't know what they actually do exactly.
Yeah, definitely. That's a good, awesome, amazing question. So I'll try to hit it all. And if I miss a part of it, just remind me. But really, I would say for me, PhD was kind of one of those things that I saw as a way to allow me to do research. I knew from, the experiences I had as an undergrad, whether it was even in astronomy or in a materials lab, I really enjoyed, coming up with new ideas for these seemingly impossible challenges at times, depending on what project you're tasked with, and really breaking it down and trying to really come to a solution to help enable, help people really is I think a lot of the core of what we do at NASA. And so for me, a PhD was really, I knew I was going to do a PhD. What was kind of funny though, is the process for me was I'm a planner. I will say that. I always like to have a backup plan. So, I was a little afraid, like, what if I don't get into any of the grad schools I applied to? Because I was applying to a materials program, right? Coming from a physics background, I was, you never know, right? So one thing I didn't really mention yet was that I studied abroad in Japan. And I also got a certificate in the language, really enjoy traveling as well. So my backup plan, if you will, was to apply for what's called the JET program. So it's kind of like a Japanese government-sponsored exchange program that allows recent graduates or others from English-speaking countries to teach and live really in Japan. And so I actually applied to that as sort of, my backup, like I said. And I was really lucky that I ended up getting not only a grad school offer or several that I could pick from, I also got the opportunity to go live and work in Tokyo, Japan, as an assistant English language teacher and translator. And so it was one of those like sticky situations, like, what do I do? Like I really want to go to grad school, but this other opportunity sounds really cool too. And so it worked out that, I informed the graduate chair at Purdue, like, hey, I have this opportunity. Any advice? Like, and so Purdue was really great. The department was really, supportive and enabled me to take a year off effectively and delay the start of my graduate program and go teach in Japan. And I share that mainly because I think a lot of people do have that image that, oh, after undergrad, I have to go to grad school. If I stop and do something else, I won't go back. And, for some people that's true and that's okay, right? But, there are other routes. I have to say that year for me was really, really important because it allowed me to do something that wasn't, so STEM focused, and what my career ultimately ended up being. Let me sample something else and also experience and live in a new culture while traveling. I got to do a lot of traveling, which was really, really important, I think, and formative for my life experiences. From there, I think it really helped me also recognize that, research is what I want to do for the rest of my life, or at least for the foreseeable future. So it really helped me get excited really for grad school too. It was kind of like a little mini break, if you will. So that's how it worked for me. And so then when I got to, I flew back from Tokyo, Japan, and within, I think, 3 days, I was moving into my apartment in West Lafayette, Indiana, right? So the culture shock was real, but it was just a fantastic experience, I think, getting to live abroad. And then, really it helped me motivate me, I think, to dig down deep and get a PhD and go to grad school in materials.
Yeah, that's great. And so you kind of explained how'd you figure out about why the PhD was right for you. And so now the evolution of that is, how did the PhD help you get to NASA? And then when you were at NASA, how did research in a lab versus NASA compare?
Yeah, definitely. So I will say you do not have to have a PhD to work at NASA. That is not the case. So I do want to make sure all the listeners know that, that it's not a requirement. There are plenty of valuable, very important roles that people play that you have either bachelor's or master's. So there are a bunch of different, really interesting career paths. For me, like I said, research was what I was pretty confident that I wanted to do for my career, which is why I went to grad school for it. I'd say the PhD itself is really helpful in training. Obviously you become an expert or you're supposed to become an expert in whatever your dissertation topic is. And also another thing that I think the PhD does that most people don't recognize is it really helps you learn how to tackle problems and think and, really approach things from a very scientific perspective, really. And in doing so, it really positions you well to tackle any problem. So I know obviously materials, there's so many different issues and problems that can come up in materials, whether it's, biomedical, aerospace in my case, right? It's a huge, very, very disparate field. And so I think getting a PhD really helps someone learn how to approach problems and really tackle them. Whether or not they end up being in materials or whatever your topic area initially was. For me, what's kind of interesting is that my dissertation was specifically for ceramic materials for aerospace applications, specifically high temperature, more like reentry vehicle, leading edge kinds of applications. For me, when I came to NASA, or at least the opportunity that came up, it appeared that it was going to actually be very, very close to what I was working on within my dissertation. And so I was really excited, like, oh, I'm going to apply a lot of what I've been doing with my dissertation work into the work that I'll be doing at NASA. As some of you all might know, things change, projects redirect or revector, or, things happen. And so it's kind of funny is when I actually ended up starting my position at NASA a number of months later, the project that I originally had the intention to support no longer really needed me. At first, I was kind of like, oh no, what do I do, right? And so this is kind of an example of, the PhD, it helps you approach new problems. For me, I was able to, similarly with ceramics, I was able to kind of revector a little bit and tackle a new project that was more related to ceramic matrix composites in an aircraft turbine engine environment. And so that's where I really jumped in at NASA. And I'd say for the most part, the experience from research and grad school to NASA is all pretty comparable in the sense that working in lab, doing a lot of the materials characterization. The big difference I would say is at NASA, there are more people to help. So when it comes to some of the activities that I would maybe do as a grad student, like polishing, I think a lot of folks remember that, prepping samples for different characterization methods. At NASA, we have really great staff that can help us either train us to do it ourselves or, help us and accomplish some of those activities for us. But I say by and by, largely, research was the environment is a little different, but the way research is done, it's all very similar. So that's been my experience so far.
Wow, that's super fascinating. And it seems like in your career journey, a common theme that's played a vital role is like networking or just chatting with people who you really respect and who you value. And it's something that we've really emphasized in previous episodes. But one thing that I wanted to key in on here is the impact of professional societies on your career. And I was wondering if you can talk to that a little bit more and just how, like, what they offer and how that's valuable to materials engineers.
Yeah, definitely. As you said, networking can be very helpful and important. I think no matter what career path you take. For me personally, the societies that I've been more active in, of course, ceramics, right? So I've been pretty active in the American Ceramic Society. I started in that society. If you guys are familiar with Materials Advantage, it's a really common membership, right, for undergrad and grad students. So American Ceramic Society, or ACERS, is one of those memberships that's included in the Materials Advantage. There's also ASM International, which is another society I've been involved with as well. Later on, since coming to NASA, another society I've gotten more involved with is the American Institute of Aeronautics and Astronautics. So that's AIAA. And so, as the name implies, there's nothing about materials on that title, right? So it is geared more towards the aerospace industry as a whole, and materials and structures being an important part of that. So there is, of course, the technical committee and activity involvement within the Society for Materials. But those are kind of the three major ones that I've been involved with. What I think is really important about networking is, for my job, right, collaboration and outreach are some of the activities I get most enjoyment out of. I really enjoy working with people on different problems. And so networking, especially in a conference environment, or even working with folks in a professional society, many of the collaborations that I have now, I actually developed through interactions with people at conferences or the professional societies. And some of them date way back to when I was actually a grad student, which is kind of funny to think, right? And so I think those connections really help down the road. And they also give people like myself perspective on what other people think are important to pursue and on different approaches of looking at, similar problems. So I think professional society involvement can't go wrong with it. That's for sure. And another thing I think that's also important with networking in general is that it really helps give perspective on other people's career paths. And so for that, whether or not, obviously, I'm sure mentoring has come up or will come up in your podcast. And so I can't underscore the importance of, having a mentor or finding a mentor. And networking in a professional society or conference environment really lends itself well to finding different people who might have career paths that, hey, you look at and you're like, I'd like to learn more about that. And I think it gives a really good way for folks to connect that way and maybe form mentoring relationships that can last longer than, just a conference. So those are some of the key, I think, benefits I see with networking and especially professional society involvement.
I feel like I know a lot about your journey now. So thanks for walking us through all that. It's very informative. But now that you've told us so much about yourself and how you got to where you are, we would love to talk to you about the science that you do in your day-to-day. So this is a material that you worked with. You called it ceramic matrix composites, or CMCs, which are preferred in high temperature applications like aircraft engines specifically. Could you kind of go into CMCs and the characteristics that make them preferred in these applications?
Definitely. Yeah, so that's right. Ceramic matrix composites offer a lot of potential in the aviation industry and aerospace and as a whole. What's kind of funny is when a lot of people hear ceramic, they might think of, like a coffee cup or, other day-to-day objects that tend to be more fragile. They don't really think about jet engines, right? And so what's kind of exciting about, ceramic matrix composites or CMCs is that, really it's basically a combination of ceramic fibers embedded within a ceramic material. And those ceramic fibers are incorporated to help improve the mechanical performance of the CMC part. And so right now, silicon carbide is really one of the leading material systems of choice right now for aviation. And what makes SiC CMCs, so SiC, silicon carbide, you got to abbreviate everything, right?
SiC,
so we would say SiC, so SiC. So if I say SiC, I'm referring to silicon carbide.
Appreciate that.
Really, right. And so what really makes silicon carbide CMCs appealing for aviation is that they're about a third the weight of traditional metal alloys used in gas turbine engines. What's more is that they can withstand much higher operating temperatures compared to some of the metal alloys being employed, meaning ultimately that less air from the flow path of a jet engine needs to be diverted to help cool the hot section components that are there. And so by that, the engine can really operate more efficiently at higher thrusts, resulting in, an aircraft engine that is more fuel efficient and having lesser emissions, which obviously is great. And so to kind of put that in perspective, there have been studies shown that the shift in materials could help improve engine efficiency by about 6%, which doesn't sound like a lot, but when you factor that in from a fuel savings perspective, this could actually result in savings of around about $500,000 per aircraft, which is really a tremendous amount of savings when you factor in the number of planes that are flying right now. So from an economic standpoint, CMCs are very attractive. And then coupled with, the environmental benefits, there's really a big driver to get CMCs flying in aircraft engines. So it's a really exciting material system. I will also say there's always an asterisk. As you might expect with just about any new technology, there's always a challenge or two. And CMCs, even though they're an outstanding material system, they are, however, susceptible to degradation due to exposure to, for example, like oxygen or water vapor, which of course are present in the turbine engine environment. So at these high temperatures, for example, water vapor can effectively attack the silicon carbide CMC, causing oxidation and volatilization of the outer surface layer, leading to recession, which isn't great. And that can obviously lead to failure ultimately. So to help protect and prolong the life of CMCs, we're doing a lot of research and developing what are called environmental barrier coatings, or EBCs, to help protect the CMCs in the hot section of the engine, as well as other extreme environments. So that's kind of, I'd say in a nutshell, CMCs offer a lot of potential and are being flown right now. There are aircraft engines with them being applied with the use of EBCs, or environmental barrier coatings.
Wow, that's really cool. I was just wondering, are there any other like drawbacks, or is like what is kind of the main inhibitor in terms of like seeing CMCs in like all aircraft engines? Is there any like process related challenges, or like from the cost side, I heard maybe that's still something that needs to be figured out, right?
Yeah, so as you can imagine, these materials having higher melting temperatures and among other things can make them more challenging to process. That being said, GE Aviation, they've kind of really almost championed the development of CMCs from an industry perspective, in that they've already done a lot of the scale up to enable CMCs to be applied in aircraft engines. It's still costly, but they've actually opened up new manufacturing sites at a large scale and are making parts that they're flying right now in aircraft engines. And so, for example, the combustor liner is one that, on some of their latest and greatest aircraft engines that are being deployed right now, they are flying with CMCs. And the hope is that with further development of some of these environmental barrier coatings or other maybe even processing benefits that we can come up with, we'd be able to really open the floodgate, if you will, to help enable ultimately, I think, I'll say kind of one of the holy grails of CMCs in the aircraft turbine engine would be to be able to enable them as a turbine blade. Mm-hmm. And so a turbine blade is a complex shaped component. And so there are design challenges that are being worked right now to help overcome that. But, so I will say that CMCs, it's exciting because they're being implemented. And there's still a long way we can take them to really fully utilize the benefits they could offer in aviation.
For CMCs, that refers to a pretty wide range of materials, just the composite ceramic composite, sorry. And so silicon carbide is one, with silicon being very valuable for its really high temperature resistance. Is most of the research going into these environmental barriers, or are there other CMCs that are possibly being looked at as maybe alternative solutions to silicon carbide?
Yeah, that's a great question. So when it comes to silicon carbide, there are some things that could be improved, right? And so really, I would say it's dependent on the application. Mm-hmm. So for example, if we're looking at, like a reusable commercial or just a reusable hypersonic vehicle, for example, for space, to make routine space access more attainable, that environment is different than what you'd see in a gas turbine engine. So there are other ceramic candidates as well that are of interest, of course. And so really, I would say that, ultimately the flavor, if you will, of ceramic you pick is very dependent on the application. Also looking at commercial aviation, oxide-based ceramics so are of interest because you don't necessarily have to worry about them oxidizing because they're an oxide, right? They already have oxygen present. So that's kind of their benefit. The trade-off, though, is they do have a lower kind of temperature envelope in which they could operate. And so it's really kind of the trade-off of finding, just even beyond ceramics, right, for any application in materials, weighing the pros and cons of a material versus how it will be used. And so different elements obviously will lend themselves better. And so kind of finding that balance, I think, is where we're at with ceramics, as well as a variety of other materials in these applications.
Yeah, when I interned at GE Aviation, it seemed like CMCs and would play like a pivotal role in like the future of aircraft engines, along with additively manufactured parts for more of the like complex areas to kind of fill out the rest of the engine. So that's really cool. And you mentioned coatings, which kind of leads right into my next question. So all of these external environmental conditions like runway dust particles or like sand, volcanic ash, that can really affect aircraft engine dramatically. So what are the consequences if these particulates get ingested into the system, and what steps, you kind of mentioned it, but like what in general are we doing to address those consequences and minimizing that risk?
Yeah, definitely. So if anyone's listening to this podcast from an airplane, don't worry, everything's okay. It'll be fine. In the sense that, runway dust is always present. And depending where you fly in the world, sand, volcanic ash particulates, they're always floating around. And it's inevitable that an aircraft engine would ingest some of these particulates. And so they're designed to, tolerate a certain amount of particulate matter. And obviously there's a lot of safety involved. So I don't want anyone to be too concerned if they're on a plane right now, especially over a desert or something like that. One thing when we look at CMCs, like I mentioned, with their higher temperature capabilities, as we look to incorporate CMC-based parts with EBCs, of course, in the hot section, the engine operating temperatures are slated to dramatically increase, rightfully so, to help improve some of the efficiency we talked about, right? And the temperatures we're talking about are close to 1500 degrees C. That's kind of what we're pushing towards, which is around 2700 degrees Fahrenheit, which is very hot, as you can imagine, right? And what makes, particulate ingestion events more concerning with these newer engines is that typically sand, a lot of these particulates, they actually melt at below, like depending on the composition, anywhere from, 1200 C to, much lower than the operating temperature. And so the concern there is not only do you have the issue of, particulates coming into your aircraft engine, there's the very real possibility, and actually it's been shown, that they can actually melt and stick and adhere to parts of the aircraft engine. And they can, from, just an aviation perspective, they can block the airflow, which is not good. Additionally, from the materials perspective, what I've focused on a lot with my colleagues at Glenn previously was looking at the effects that this molten sand, for example, would have on the coatings themselves that are designed to protect CMCs. Because at these high temperatures, you get thermochemical interactions, meaning that new phases, new materials can actually form at that interface where the sand melts on, your coating. And so there's a lot of research in the community trying to address this. And so, and just for everyone's awareness, if you want to look up more about it, the kind of the acronym, because of course acronyms are everywhere, for this particulate research area is called CMAS. And it's actually CMAS, and it stands for calcium magnesium aluminosilicate. So that's a mouthful, right? So everyone defaults to CMAS. And I wanted to share that because the reason that acronym was selected is because, believe it or not, sand, volcanic ash, no matter where you are in the world, pretty much, the dirt that's around you, I know we don't always think about it, has a very similar composition. There are, of course, differences depending, but at the end of the day, they all kind of contain calcium, magnesium, aluminosilicate, CMAS. So that's why we usually group it there. So it's a really exciting area of research in the sense that it combines a lot of interesting materials, thermodynamics, thermochemistry, physics issues, a lot of that kind of stuff, if that piques anyone's interest. So it's an area that a lot of people are targeting to help really enable and improve the safety of these next generation aircraft engines.
That's so interesting. My next question to you was going to be, how does it affect the microstructure? But you kind of alluded to that. I guess one follow-up question would be, I don't really think that I've seen any entire engines being replaced because of this yet. Is there have we started to research at what point maybe the barrier should be changed or something should be replaced? Or are we trying to just right now understand how it affects it? And potentially it could be a non-factor for the lifetime of the plane currently, but maybe it would have other issues in certain use cases.
Yeah, there's been some really interesting, I say, studies, and really, so particulate ingestion events have actually been a problem ever since aviation, really, especially with the jet engine. And there have been well-documented events I can think of some from the 70s and 80s that have caused significant issues with aircraft. And back in, I think it was around 2010, some of you might remember there was a volcano eruption in Iceland, and they still sometimes have issues with this. This one in particular, the eruption went on, and the way the volcanic ash plume traveled, it basically covered continental Europe and effectively shut down airspace for almost a week, commercial and military. And so because, like you mentioned, how much an aircraft engine can tolerate, it's not super well understood. And so there's been a lot of effort, especially since that particular event, to understand, right? There have been some scaled studies. So I think it was around 2014, NASA was a part of a larger scale effort called VIPER, which was the vehicle integration, I think propulsion research. You have to fact check me on that one. But it was a larger scale ground demonstration of a commercial engine, and they effectively fed volcanic ash through it and ran a bunch of different simultaneous diagnostics to see how it impacted performance. And so that's one example of a very high scale, like a very, we're working with an aircraft engine to understand what's happening when ash is being ingested. Then on the opposite end of the spectrum, you have where I kind of play a bit is what's happening to the material, right? So at a microstructural level, what materials are going to form? What is that going to do to the engine? How much is needed for that reaction to take place? Does it help us? Does it hurt it? All these questions, right? You have to kind of get to the bottom of. And I think that's where research is so fun, right? No matter what end of the spectrum you're on, I think it's really important to keep, the bigger picture also in mind to help tackle and help us really enable these materials and get to the point where we have a good understanding of, oh, this volcanic eruption, it's no big deal, go ahead and fly, or don't go there, or reroute to somewhere else, right? So that's, I think, kind of where it is right now. So there's still potential. There's been interesting work, but there's still some room for improvement, if you will.
Yeah, it was interesting. One thing I learned during my internship was that for like aircraft engine manufacturers, the industry as a whole, a significant driver of revenue is actually like the maintenance side of things rather than the sale of the engine itself. And now it kind of makes sense that like there's so many considerations, and sometimes you have to replace components and just ensure that it meets all of the safety standards, since it's such a heavily regulated like market and environment. So that's really cool. Thanks, Valerie.
Mm-hmm.
Cool.
Yeah, that'd be pretty cool if it turns out that volcanic ash helps. So all the finishing processes, you throw a bunch of ash in your engine right before it flies. But yeah, so that's a lot about on Earth. But another thing about NASA is that you're looking in space. So in space, lunar dust, for example, is very jagged, abrasive, and sticks to everything that will land on the moon. So what characteristics would make an ideal ceramic coating for space? And kind of walking through how do we kind of like almost design for a completely new environment that we're not currently on.
Yeah, definitely. So one thing I think that's helped me, for example, with my research was, starting and looking at the effects that volcanic ash, sand, those kinds of particulates have in an aircraft environment. What about the other extreme environments out there, right? Like lunar dust, for example, like you said, is a really tricky design challenge for a lot of the efforts that are being made to enable a sustainable human presence through the Artemis missions that we're really championing right now. And so for me, what I recognize as a design opportunity, really, it's a challenge and an opportunity, is that ceramics, for example, I mentioned people usually think of ceramics as being brittle, but there's a wide design space of advanced ceramics that actually have very impressive mechanical properties, depending on what kind of application you're looking at. And so for some of the ceramic coatings, I've kind of come up with the idea that on Earth, we're using a lot of ceramic coated parts in really aggressive applications like, deep sea drilling, mining, machining, and ceramics have really proven their mettle there. And I think that no one obviously, or to my knowledge, and I think most people would say, no one has sent ceramics to the moon for protective purposes. And so the idea being we can look to some of the ceramics that are being used in these more, terrestrial, earth-based, aggressive applications. How can we learn from those and help learn from them to help us learn how to enable them on the lunar surface in different applications? And so there are some ceramics that offer pretty impressive erosion protection, as well as wear from particulates. And so we've been kind of looking at those particular ceramic compositions and trying to kind of tailor them and develop them for applications on the moon to help protect, whether it be like a lunar rover vehicle, a habitat, or a landing vehicle, trying to come up with ways to help improve a lot of the performance of these kinds of technologies. And so from there, the idea being that with these ceramics, we'll be able to offer a longer life, a use life, right, on the moon compared to some of the materials that are being used right now.
Wow. That kind of leads me to my next question. And we mentioned in a previous call, you and I, that we're going back to the moon and we're going to make it more sustainable this time. And so I was wondering if you could kind of talk to that a little bit, like what role does materials engineering play in helping NASA achieve a more sustainable lunar mission next time?
As a materials scientist and engineer, there are so many different considerations we have to make when we're looking at different applications, right? And the way I think a sustainable lunar mission really offers a lot of potential for materials that haven't been explored before, mainly because we just really haven't had that many opportunities, right? Haven't had a crewed mission to the lunar surface since the early 70s. And so this time going back to the moon, I think everyone, not just NASA, but I think a lot of people agree that it'd be fantastic. We should really make this opportunity to make a sustainable presence, to enable us to go back more than once, right? Instead of a one-off. And so materials really, I think, are kind of a key enabler there, in that we can ensure that the material performance can be improved by looking at some of, since the 70s, right? There have been a lot of advances in materials design and development. And so looking to those kinds of opportunities to prove out some of these newer materials, I think will really help us get to the point where we can have a sustainable lunar presence. And so right now we're really putting in place a plan to help us kind of vet some of our new materials. For example, there's several upcoming missions we have what's called the Commercial Lunar Payload Services, CLPS is what we call it, where commercial entities will actually be sending payloads up for us to the lunar surface, where we can actually deploy some of our materials in the lunar environment and see how they behave. Because as you can imagine with materials, it's really important to test them. And replicating the lunar environment on Earth is really hard. So being able to send materials up there directly, I think, is going to be a really cool opportunity to get a better understanding of how these materials can really help enable our missions that are coming up on the moon.
I was about to ask, you don't have to go into much detail, but I was going to ask what that materials development and testing process looks like when you're operating in the space conditions. I don't know to what extent you're allowed to talk about that.
So I can talk about that. So obviously from the lab scale to full implementation, you've got to vet the material as best you can, right? And when you work with these more harder to replicate, whether it's space, even a gas turbine engine is a pretty aggressive environment too, right? So the way we usually look is a lot of times it starts more of at the coupon level, right? We'll do smaller scale tests, whether it's mechanical, looking at different environmental concerns. So for example, with the ceramics work for coatings for lunar applications, we're looking at, wear and erosion, as well as stability under cryogenic temperature. So the lunar surface it can be hot or cold, depending on if you're on the sun side or in shade. So being sure that our materials can tolerate those kinds of quick thermal changes are really important. And ultimately, for my activity, what we've kind of targeted as a demo article, if you will, is looking at, for example, lunar lander vehicle. What would happen if we coat it, a lunar landing, like just a leg, if you can picture, Apollo, the eagle, the kind of the spider-like legs, right? If we coat that with the ceramic, what will that help us enable a reusable landing vehicle? We're not at that point where we can actually put it on a landing vehicle. But some of the next logical tests we're trying to put in place are, from a processing side, can we coat something that large? Because the legs, depending on the concept, are, up to 10 feet tall. How would we, address that? And then add the different loading events. So landing obviously is an impact event. So will our material be able to handle that as a coating? And then of course, lunar dust, like we talked about, that's kind of the big focal point for us, is with these, with the landing, when you're that close to the engine, so you get like a rocket plume. And that plume kicks up a ton of ash. And so the particles themselves can be going upwards of 2 kilometers per second, which is just unreal when you think about it. Super fast, right? So very aggressive environment. So one thing we're kind of grappling with right now on Earth is how do we replicate those kinds of particulate speeds and basically shooting them at our materials. So we're looking at different ballistic tests to help
Mhm.
kind of understand, material performance under those kinds of conditions. So that's kind of more of a mid-grade test, I would say. And so the idea being we kind of work our way up to the point where, okay, we've at least checked all these boxes that we can kind of hang our hat and say, we think it should be able to tolerate a lunar environment. And that's just kind of how it works, I think, across the board for a lot of materials technologies. You got to kind of prove it out at the lower level and then kind of make progress to demonstrate that it can handle, the ultimate application.
Yeah, I didn't think about trying to coat a 10-foot leg, especially when you're trying to cover all surfaces evenly to make this perfect coating, or else you could run into issues. So I that sounds very difficult, at least.
It's fun.
But yeah, talking about that, it's like challenges and things such as this are inevitable in no matter what field you go into, and especially when you go to space. I feel like there's going to be a lot of challenges, but a lot of challenges lead to personal growth. And so, as your role as a research materials engineer at NASA, could you kind of explain maybe one or two of like the hardest challenges you've overcome and how that kind of affected your personal growth as well?
In life, there's always challenges, right? And as you go along in your career, things will come up. And I would say probably one of the ones that I think that I've encountered have been related to navigating life and work, of making the transition from school to career, and then even within the career, how do you grow and evolve in your career path, right?
Mhm.
And so for me, one of the things that was challenging at first, and I think has really turned into an excellent opportunity for me, was started at NASA Glenn Research Center, which was in Cleveland. And now I'm at Langley, right? So it's like, how did that happen? Well, long story short, my husband and I, we kind of faced the two body problem, right? So trying to find career opportunities that suited both of us was kind of a challenge. And we wanted to be, of course, living in the same location. And so when it became apparent that Glenn, there might be more opportunities outside of, the northern Ohio area, we had to kind of start evaluating some of our options. And I would say, I think what was really helpful for me was that I had a very supportive work environment. I was pretty open with my supervisor about, what kind of opportunities could there be in other places. For example, NASA Langley, since my husband had some career prospects there. And so navigating that, switching centers, because I admittedly didn't have any plans to leave Glenn. I thought I was going to be Glenn forever. And so, the realization that, I may have to switch centers, and this will impact probably the research I do. Because each NASA center does, we all collaborate and work on problems together, especially in materials. That being said, each center does kind of have its core competencies, right? Coming to Langley, I had to kind of get, it was like starting over again in a sense, right? Like figuring out the lay of the land, what people do, what research is in, which is available and, interesting to me. That was kind of a challenge, trying to figure out where I could fit. And looking back, it's one of those things, hindsight is 2020. Because at the time I was really nervous, like, oh my gosh, what if I can't find anything interesting to work on, which is kind of hilarious because I work at NASA and we do so many cool things, right? I think learning, getting the experience and opportunity to be adaptable in a professional environment, I think is really, really a good opportunity for anyone. And so I think the challenge that I faced was identifying what areas would be, where can I make an impact? Where can I help people, right? And thankfully, Langley has a really strong, obviously, heritage in materials, especially for extreme environments. I was able to really, I think, dive in and really work with really great people. So that's been, I'd say, a really rewarding experience for me. So yeah, that's one challenge. Did you want another challenge?
No, I think that's good. That
Okay, cool.
No, that's definitely very like important to consider, because I think like from the student side, there's just, for material science specifically, there's just so many different potential options. And then even within like the aerospace industry, it's such a vast field that you can be like a systems engineer, process engineer, research engineer. So I think that was very helpful, and you've already shared so much advice for us and our listeners, but to kind of wrap up this episode, do you have maybe one final piece of advice for MSEs who want to pursue a career at NASA or in the aerospace industry as a whole?
Yeah, definitely. I was going to say, I'm super biased, right? Working at NASA in aerospace materials. I really think now is the most exciting time to be a materials scientist and engineer in aerospace because of all of the amazing, amazing opportunities there are for using materials or looking at materials in different ways for different applications, not just on Earth. We're talking moon, Mars, beyond, right? And so that alone, I think it's just very, very exciting time to be in materials. And so my biggest advice really would be to keep an open mind, along the lines of the challenge I just shared. And even, earlier on in our conversation, keeping an open mind to new opportunities, I think is really important and will help you no matter which career path you take, whether it's in industry, academia, government, that kind of thing. Even if you decide not to go into aerospace, which I'm like, come on, aerospace material is the best, right? But I think keeping an open mind to new opportunities is really going to take you far, because at the end of the day, if you try something, even if you're not, for sure about it, like for me with materials back when I was an undergrad, you never know where it's going to take you. So I would just say, keep an open mind.
I love that. I feel like you're trying to convince David and I to also join the aerospace industry. So.
It's fun, guys. It's a really fun thing.
You're doing a good job. But yeah, thank you so much, Valerie, for joining us today. That was a wonderful episode and I learned a lot. So we really appreciate you having you on the show.
Thank you again. It was really fun talking with you guys.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.